Bismillahirrahmanirrahim. Hello students, welcome to the electrical engineering channel. So as a continuation of my previous discussion of Simpson's 1 by 3 rule of integration, I will today demonstrate Simpson's 3 by 8 rule of integration. And Simpson's 3 by 8 rule of integration actually starts by the assumption that the complex mathematical function is approximated by a third order polynomial. So every function can be represented in the form of n order polynomial. So in Simpson's 3 by 8 rule, we will consider that our function is equal to the third order polynomial. And in this case, we have to evaluate the values of these four coefficients, a0, a1, a2, and a3. And these four coefficients can be evaluated by considering 4 points on the function. So this is our function suppose, and the first point is actually point A, which is the lower limit of integration, and one point is the last point of the interval of integration, and 2 points will be considered within these 2 points, right? So this is our third point and this is our fourth point. So x0, x1, x2, and x3, these are our 4 points. And by considering these 4 points, we can clearly see that the Simpson's 3 by 8 rule will be based on three segments of the function, right? This is first segment, this is second segment, and this is the third segment. So we have three segments. So the step size in this case will be equal to b minus a divided by 3. So this thing can also be observed in this figure. This is our third order polynomial approximation of the function, and we have to consider these 4 points, and these 4 points on the function will give us three segments, right? So let's substitute these 4 points in the function, and then we will have to evaluate the values of these four coefficients. And we have 4 points, so we will have four equations, and those four equations can be solved simultaneously to evaluate these four unknown coefficients, and that won't be too different from what we discussed for Simpson's 1 by 3 rule. So this is our f of x naught, f of x1, f of x2, and f of x3. And also x naught is equal to a, right? X1 is equal to a plus h, x2 is equal to a plus 2h, and x3 is equal to a plus 3h, which is equal to b. And h is equal to b minus a over 3. So let's simplify this, and it will become 2a plus b over 3. X2 will be equal to a plus 2h, and it will be a plus 2b over 3. And x3 is equal to a plus 3h, which will be equal to a plus b minus a, or it will be equal to b. So these four equations can be written in the matrix form as follows, and these are our four unknowns, and these are the right hand side column vector. Okay, so these four unknowns can be evaluated by using MATLAB again, and this is the code. And here we have a, b, f of x naught, f of x1, f of x2, and f of x3. These are our six variables, and this is our a matrix, this is our b column vector, and x will be evaluated by using this command line solve a b, and then we will simplify this x, and we can display the value of the x. So this x will contain all the four unknown coefficients, and we can substitute those four unknown coefficients in the integration of this polynomial expression, and then we can get our final answer, right? So four unknowns are evaluated, and the integration of this fourth order polynomial will be equal to this expression, and this is very simple expression. And in this expression, these four unknowns can be substituted, and finally we will have this expression of the integration. So this will be equal to b minus a divided by 8, f of x naught plus 3 f of x1 plus 3 f of x2 plus f of x3, right? So this whole derivation is extremely difficult if we perform this by our hand, but by using MATLAB, this derivation can be done in just a matter of seconds. Okay, so this is what MATLAB has given to us, right? So this is our a naught, and you can see this is extremely long expression for a naught. and this is A1, this is A2, and this is A3. So these are extremely long expressions of the four coefficients. And the next step is to substitute these four unknown coefficients in this integration expression, right? So integration expression is this equation number one, and we can also observe it over here. So this is our function, and its integration is given over here. Okay, so this is the integration, and those four unknown coefficients a naught, a1, a2, and a3, their values have to be substituted in this expression, and then again a simplification has to be carried out, and that simplification is done by using MATLAB again. So here you can see that these four coefficients. So x is the column vector, and that column vector contains x no x0, x1, also x1, x2, x3, and x4. So x1 is actually a naught, x2 is actually a1, x3 is actually a2, and this is a3. So after putting these values in this expression, we will get the integration. So that integration is equal to this expression. So luckily this expression is quite simpler, and it is equal to b minus a divided by 8 into f of x naught plus 3f of x1 plus 3f of x2 plus f of x3. Okay, so this is the same expression which I have written over here and here as well. So this expression. So in this case, h is equal to b minus a divided by 3. So b minus a will be equal to 3h, and we can substitute this value of b minus a in this expression, and it will be equal to 3h by 8. So clearly, you can observe 3 by 8 written over here. Okay, so due to this multiplier term of 3 by 8, this rule is called as Simpson's 3 by 8 rule. In our previous lecture, we discussed Simpson's 1 by 3 rule, and in that lecture, we observed h by 3 over here. So here we had 1 by 3h. So that's why that method was called as Simpson's 1 by 3 rule. And here we have 3 by 8 over here. So that's why this method is called as Simpson's 3 by 8 rule. So that is our final expression, and based on this three segment Simpson's 3 by 8 rule, we can extend our discussion to multiple segments, so sigma Simpson's 3 by 8 rule. And in this case, the number of segments must be an integer multiple of 3. Okay, so we can divide our whole domain of A to B in a multiple segments, and on each three segment section, we can apply three segment Simpson's 3 by 8 rule, right? So suppose we have our domain from x naught to xn. So for first three segments, we will apply Simpson's 3 by 8 rule. These are the next three segments, and so on, and these are the last three segments. So let's apply Simpson's 3 by 8 rule over here. So I will be equal to 3h by 8, f of x naught plus 3f of x1 plus 3f of x2 plus f of x3. So this was the answer for the first three segment integration. For the next three segment integration, we will have of f of x3 plus 4 plus 3f of x4 plus 3f of x5 plus f of x6. Right. So these two terms will be added together. Similarly, f of x6 plus fx6, they will also be added together, and they will become uh, this expression. So first term will be alone, last term will be alone, and for I equal to 1, 4, 7 up to n minus 2, we will have a multiplier term of 3, and for I equal to 2, 5, 8 up to n minus 1, we will have a multiplier term of 3, and for the terms which are multiple of 3, we will have a multiplier term of 2, so that will be the general form of the Simpson's 3 by 8 rule summation. So by using Simpson's 3 by 8 rule, we can evaluate integrations, and I have done it by using MATLAB, right? So this thing has also been discussed in this lab manual, and here we have examples. This is the example of Simpson's 1 by 3 rule, and here you can see we have h over 3. That's why this rule is called as Simpson's 1 by 3 rule. And for multiple segments, so Simpson's 3 by 8 rule, we will have this expression which I have also discussed. And here uh, we have to write a code. This is the code for Simpson's 1 by 3 rule, and this is the code for Simpson's 3 by 8 rule. And by using this code, we can apply both these rules and evaluate the integration, right? So by using Simpson's 3 by 8 rule, from t equal to a to t equal to 30 seconds, the distance can be evaluated. So I have used 3 segments and 6 segments Simpson's 3 by 8 rule. So this is the code for Simpson's 3 by 8 rule. So let's evaluate this integration by using Simpson's 3 by 8 rule and draw the comparison with the exact integration. Okay, so let's run this code, and after running this code, this is the answer. This is the exact answer. This is the answer given by Simpson's 3 by 8 rule with 3 segments. And for 6 segments, again I will run this code, and now you can see my answer gets closer to the exact answer. So one important thing to be taken care of is that in Simpson's 1 by 3 rule, our total number of segments must be an integer multiple of 2, or they should be an even number. And in Simpson's 3 by 8 rule, our total number of segments must be an integer multiple of 3. So for example, 6 or 9 or 12 or 15, these number of segments can be used for multiple segment Simpsons 3 by 8 rule. So here you can see when I increase my number of segments to 9, my answer gets even closer to the exact answer. So that is all about our today's lecture of Simpson's 3 by 8 rule, and I hope that lecture was quite understandable to you. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.